so that's record. We're good. Carbonyl chemistry. Aldehydes, ketones, carboxylic acids, and so on. I don't think that's the right. There we go. Carboxylic acids and so on all share similar function and structure. So we're going to let R be sort of any alkyl or aryl group, benzene ring or something like that. And then we're going to have group Y, and we're going to let group Y be basically whatever. So if group Y is a hydrogen, that's an aldehyde. If it's some kind of alkyl group, that's a ketone. Here, just so you know, this line represents the bond between hydrogen and the carbonyl carbon. The little squiggly line just represents the fact that we haven't drawn this over here. Other things that you might see, maybe the Y group is a benzene ring. Maybe it's an OH group. In that case, it's a carboxylic acid. Maybe it's an NH2 group or some NHR group. In that case, it's an amide. Maybe it's a halide, or maybe some kind of OR group. That would be an ester. Maybe it's an SR group. That would be thioester. And then in biology, sometimes you'll see a phosphate group attached to the carbonyl carbon, and that's sometimes called an acyl phosphate or perhaps a phosphoanhydride. But all of these compounds share the basic structure of a carbon doubly bonded to an oxygen. Now, some of you may have had some experience with molecular orbital theory, others of you may not, and that's okay. I tend to use it as a way to help us remember what happens and why in organic chemistry. And I will post sort of a review study guide with some information about MO theory if any of you want to review that. What you might expect from carbonyl chemistry is that the oxygen is more electronegative than the carbon, and so you would expect the function of a carbonyl to be governed by a partial positive charge on the carbon and a partial negative charge on the oxygen. In other words, if you had to pick, if this molecule were going to act as an electrophile, you would predict, in terms of being an electrophile, it would react here, but if it were going to be a nucleophile, it would react on the oxygen. Another way of saying that is that the highest occupied molecular orbital of this molecule is the pi star, the antibonding orbital between carbon and oxygen. What that looks like, if you do the calculations, what that looks like is, looking down from the top, we'd see a large lobe here, a node in between carbon and oxygen. We're using color here just to represent orbital phase. There'd be a node in the plane of the page, and then below we'd have orbitals with this phase. And if you looked at the molecule from the side, sort of with the Y group coming out at you and the R group going back into the page, you'd see something that looked like this. And that would be the pi star of this molecule. Color here represents sign of the wave function. In any case, this is the and I said this exactly wrong, so I apologize for that. The lowest unoccupied molecular orbital. This is the place that will be attacked by a nucleophile, is this pi star. Sorry about that for getting confused. One of the things you'll notice, if you did calculations, you would discover that most of this empty antibonding orbital is on the carbonyl carbon. And so what that means is that when a nucleophile encounters a carbonyl compound, it will attack at the carbonyl carbon. It will attack the pi star at the carbonyl carbon. And what that does, when you fill an antibonding orbital, it breaks the corresponding bond. And so we'll show with an arrow the electrons in the carbon-oxygen pi bond moving out onto the oxygen. Okay, that's how nucleophiles will generally react with carbonyl compounds. Now, what about if a carbonyl compound were to act as a nucleophile? Well, the highest occupied molecular orbital of the carbonyl compound is actually the lone pair electrons on oxygen. So if you were to expose a carbonyl compound to some kind of electrophile, let's just keep it simple and say some kind of acid, the thing that's going to happen is the most reactive electrons in the carbonyl compound are these lone pair non-bonded electrons, and they are going to be the ones that react with the electrophile. In this case, it's an acid. Okay, questions about that brief overview so far? Okay, general principle of OCHEM that you learned in 351, nucleophiles react with electrophiles, molecules with high energy electrons react with molecules that are electron deficient. That is the same thing as saying molecules with a high energy, highest occupied molecular orbital will react with molecules that have a low energy unoccupied orbital. Okay, so in the next few chapters, we're going to focus on reactivity of carbonyl compounds in terms of electrophiles. So there's going to be many reactions, and you're going to feel like if you try to memorize them, you're going to feel like you get overwhelmed pretty quickly. Instead, I want you to focus on the overall theme and see in each example the pattern that I'm going to show you. Most of the reactions we're going to deal with are going to follow the following couple of steps. First, nucleophilic attack on the carbonyl carbon. At the carbonyl carbon, and we'll say we're attacking the carbon-oxygen pi star. Okay? So as we said above, when that happens, the nucleophile dumps its electron density into, and let's just say the nucleophile is negatively charged, dumps its electron density into the pi star. That breaks the carbon-oxygen pi bond. Notice that in the carbonyl compound, the carbon is sp2 hybridized, which means the geometry around this carbon is trigonal planar, right? So the carbonyl compound is flat. However, when the nucleophile attacks, we now have 4 things attached to the carbonyl carbon instead of 3. So that carbonyl carbon becomes sp3 hybridized, and its geometry is tetrahedral. And so we call this the tetrahedral intermediate. All right. And that's an important intermediate in most of the reactions of carbonyl compounds. In fact, I can't think of any counterexamples. All right. So the issue with the first step, when the nucleophile attacks at the carbonyl carbon, is going to depend on the strength of the nucleophile. So strong nucleophiles, and let's say it's as reactive as an alkoxide, strong nucleophiles can attack directly, as shown above, to give you a negatively charged tetrahedral intermediate. By the way, a brief review of nucleophilicity, what makes a nucleophile good. Strong nucleophiles are conjugate bases of weak acids. They are reactive and have high energy electrons. So you can use stuff from chapter 2, pKa, intuition, to sort of rank nucleophiles. If you recall, the pKa of an alcohol or 16. So, and the conjugate base of the alcohol is OR minus or OH minus. So things that are stronger nucleophiles than OR minus might include like H minus. We'll return to that a little bit later. I forget what the number there is. I think it's around 30. Or perhaps some negatively charged alkyl group. That pKa is around 50. So you can judge the strength of a nucleophile by remembering what you know about acidity. Weak, really exceedingly weak acids are conjugate acids of really strong nucleophiles. So if the nucleophile is strong enough, is as reactive as a negatively charged oxygen, then you can attack directly. Okay? Sometimes this first step isn't, well, we'll talk about that in just a minute. Okay, so some examples of nucleophiles that attack directly. We said OH minus, OR minus. We're going to see that when we want to use H minus as a nucleophile, we can't use that directly because it's not particularly soluble. We'll have to attach the hydrogen to something that's less electronegative than hydrogen. An example is this lithium aluminum hydride or sodium borohydride, and we'll talk about what these things do in a little bit. And then other examples are negatively charged carbons. We'll talk about what these are in a little bit, but they're called organometallic reagents, and they basically work as though you've got a negative charge on a carbon. Okay, so that's the sort of attack directly situation. In contrast, weaker nucleophiles sometimes need catalysis. What do we mean by that? Well, weaker nucleophiles may not be strong enough to attack the carbonyl carbon directly, and so you need to do something to the carbonyl carbon to make it, you need to do something to the carbonyl compound to make it more reactive. So an example of that might be acid catalysis. Okay, and there are a couple of examples, a couple of different ways that you can do acid catalysis. One would be to protonate the carbonyl compound first with a strong acid. Remember, when you use the carbonyl compound as a nucleophile, the lone pair electrons are going to be the ones that do the attacking. So you can have lone pair electrons on the carbonyl oxygen, attack the acid, and if you do that, you generate this protonated oxonium ion. That's what it's called when you make a positively charged carbonyl compound. This is an oxonium ion. And then you have the conjugate base here. Usually this is a reversible equilibrium step. And that oxonium ion is now super reactive because you have a positive formal charge on an oxygen that's more electronegative than carbon, and you can draw a resonance structure in which the oxygen is neutral and the carbon is positively charged. What this does is it makes the carbonyl compound even more reactive at carbon. It lowers the energy of the carbon-oxygen pi star, and now weaker nucleophiles can attack. And we would show that from either of these resonance structures, pointing the nucleophile attacking the carbonyl carbon, attacking the pi star at the carbonyl carbon, breaking the pi bond. We could also show from this from a different resonance structure an equivalent mechanism where the nucleophile would attack the carbonyl carbon. And then notice that we get a tetrahedral intermediate. Sorry. Only this time, the tetrahedral intermediate is not negatively charged. Why? Because we've already protonated the oxygen prior to attack. Okay, questions so far? Yes?
Why would the conjugate base of the acid act as opposed to the nucleophile?
So let me see if I heard that right. Why doesn't this conjugate base, why doesn't this conjugate base A do the attacking? Sometimes it will. Yeah, we're being very general, and in some cases we'll use hydronium as the acid, and in the second step water will attack. It will just depend on the identity of the nucleophile that we want to use and the identity of the acid. So yeah, that's a good thing to be aware of. Other questions? Don't be shy. Yes?
So are these both SN1 reactions because they have intermediates, or is that first?
Okay, so the question is, are these both SN1 reactions because they have intermediates? They are not, well, it's a whole family of reactions, and if you want to classify them, what we're going to see happen is these are either addition reactions or substitution reactions. So what I've shown you so far is just the first step. This first step is an addition reaction because we add the nucleophile to the molecule. We add two things together and we only get one. Now, whether or not it's an addition reaction or a substitution reaction is going to depend on what happens to the tetrahedral intermediate in the next step. And we're going there in just a sec. Okay? What else? Yeah? Is there any change to the stereochemistry?
When it goes from the trigonal planar to the
Yes, when it goes from trigonal planar to the tetrahedral intermediate, you'll notice that, yes, we have, depending on the identity of the Y group and the R group and the nucleophile, we have the potential to have made a stereocenter, okay? And when we make a stereocenter on a carbonyl compound, because the carbonyl compound is planar, we can either add from above or below. We're going to get both enantiomers, asterisk, because there are occasions where we can get one enantiomer over the other. You've learned in 351, no doubt, that if you don't use chiral reagents, you cannot make one enantiomer over the other. You can't get stereochemistry out of nothing. If you use a chiral reagent, you can favor one enantiomer over the other. So just to answer that question, let's imagine a specific situation. Here is a ketone. Let's put a benzene ring there. And we will use a reducing reagent. This is sodium borohydride. Don't worry about the mechanism yet. We'll deal with that, but just realize that this is a molecule that can add H- to a carbonyl compound. So there are two possibilities. We can add the H- from, we can add the H- from above to get this stereoisomer, or we can add the H- from below to get this stereoisomer. Okay, does that answer the question? Good. We will see that if we use a chiral reagent for delivering this H-, we can actually favor one side over the other. Biology does this all the time. A little bit later on, we're going to talk about NADH and what that does and how it can prefer one enantiomer over the other. All right, others? Okay. So I told you there are a couple of different ways that acid catalysis could work. it has to do with issues of reaction kinetics, and it's pretty well understood, but we don't need to go into it now. And I don't expect you to know this, but when you protonate the carbonyl first and then in a second step the nucleophile attacks, this is generally called specific acid catalysis. You won't necessarily encounter that term again until biochemistry. There's another alternative, and that is that the nucleophile attacks at the same time as the acid protonates the carbonyl carbon. What we would call that is, we would show the nucleophile attacking the pi star, the pi bond breaking, with electrons moving on to the oxygen, and then lone pair electrons on the oxygen at the same time attack the acid, and in one sort of concerted step, you add, oh shoot, like that. In one concerted step, you add the nucleophile and you protonate the carbonyl oxygen. And this happens a lot as well, and in terms of whether one happens or the other, there's a lot of factors that are involved in that, and I'm not going to ask you to predict whether it's one or the other. If the acid gets added at the same time, if the carbonyl oxygen gets protonated at the same time as the nucleophile attacks, that's called general acid catalysis. So those are the two sort of options. You can protonate first and the nucleophile attacks, or you can do it at the same time. As to which one is favored, it won't really matter for our purposes. And sometimes, to save time, we will just draw general acid catalysis, even if the kinetic evidence suggests that the acid step comes first. It's really an issue of what's the rate determining step of the reaction. In specific acid catalysis, protonation is fast, and then nucleophilic attack is slow. In general acid catalysis, nucleophilic attack and protonation are competitive, and they both sort of happen at the same time. And those are subtle issues that we just flat out won't worry about. Examples of nucleophiles that do this, these will be nucleophiles in general that are weaker than a negatively charged oxygen. Okay, so examples might be water or an alcohol. Notice that water or alcohol, the conjugate acid is hydronium, or the oxonium protonated alcohol, and that pKa is -2. Other nucleophiles that tend to be weaker include amines of various varieties. The conjugate acid of an amine is an ammonium. I'm running out of space. And these have pKa's in the sort of 9 to 11 range, depending on structure. CN minus is another example. Its conjugate acid is HCN, which I believe has a pKa around 9. So, and another, I suppose, example might be thiols, thiolates, negatively charged thiolates that are conjugate bases of thiols whose pKa's are around 8. So basically, things that are less reactive than hydroxide or an alkoxide will generally need to protonate first or during, because otherwise attack of the nucleophile is too slow. Okay. Questions so far? Yeah?
And you said those are usually pKa's of less than 16?
That's right. Yeah, or rather, molecules whose conjugate acids have pKa's less than 16 are generally on this list. Okay, and that's going to help you work your way through mechanisms, because you're going to see the text is going to show you mechanism after mechanism, and sometimes you'll protonate first and sometimes you won't. The text doesn't necessarily explain that, but this is why. Okay? All right. Others? And that was just page 1, and I've got like 8 pages today, so we're doing great. Okay. No, we don't need to get all 8. And generally, the syllabus has a schedule for what I intend to do. We may need to play loosey-goosey with what chapter's on what day because of taking time to really talk about the issues that are important to you. And so if I need to make adjustments to due dates of various assignments, I will do so on the fly and make sure you know about it. You'll never be penalized because I change deadlines around. Okay, so first was attack of the nucleophile. Next is fate of the tetrahedral intermediate. You will soon learn about me that I'm kind of a Star Wars nerd, and so I'm imagining these as sort of Star Wars titles. Attack of the nucleophile, fate of the tetrahedral intermediate. Thank you for the charity laughs, I appreciate that. I'm coming off a whole break of being with my teenage sons entirely too much, so it's good to be back among some more mature people. Let's see. All right, so fate of the tetrahedral intermediate. Let's start with a negatively charged tetrahedral intermediate, and what we learn for this one will be useful when we deal with a neutral tetrahedral intermediate. So we've got, in the tetrahedral intermediate, you got a negatively charged oxygen, you have a nucleophile, oops, that's not what we wanted to do, and you have whatever this Y group is, okay? So these are the key players in the tetrahedral intermediate. And we're going to ask some important questions along the way. Scenario 1, or A, I suppose, is Y minus is a good leaving group. Okay, well, good is always relative to, good is sort of a relative term. So what do we mean by good? Well, it's a good leaving group relative to a negatively charged oxygen. Because ultimately we're going to ask, is it better to have the negatively charged oxygen in the tetrahedral intermediate, or is it better for the Y group to leave and have the negative charge on the Y group? So is it a good leaving group relative to a negatively charged oxygen? Again, you can use your pKa intuition. The conjugate base of a negatively charged oxygen is an alcohol, pKa of 16. So Y groups that have conjugate acids with pKa's less than 16 are good leaving groups relative to a negatively charged oxygen. The second issue is the Y group a good leaving group relative to the nucleophile? Okay, and again, you can compare pKa's to determine that. If the Y group is a good leaving group relative to the negatively charged oxygen and relative to the nucleophile, then what happens is a subsequent elimination step. Okay? So what do we mean by this? Perhaps you learned in 351 about elimination reactions in which you have a leaving group at, oops, I wanted to highlight, not color. You have a leaving group here. We'll call this the alpha carbon and the beta carbon. The alpha carbon's attached to the leaving group. The beta carbon is adjacent to it. And you've seen a reaction where you remove the proton. Then these electrons kick down to form a new pi bond, and the leaving group leaves. You may not have had it explained to you in these terms that as you break this carbon-hydrogen bond, the electrons from that carbon-hydrogen bond dump themselves into the carbon leaving group antibonding orbital, a sigma star, thereby forming a new bond and breaking the old bond. This kind of reaction, so that's like the E2 reaction. You've seen that before, right? No, you jettisoned everything over the break, and you have no idea. Okay, vaguely familiar. We call this beta elimination. Now look at what we've got for the tetrahedral intermediate. You have a leaving group. Oh shoot, I guess to have our analogy be similar, we're going to make the leaving group yellow. You've got a leaving group here attached to the carbonyl carbon. For our purposes, we'll call this alpha right now. The oxygen is beta, and the oxygen is negatively charged, right? So we're sort of catching this intermediate at the spot. Apple Pencil battery is low, 5% remaining. Good, 5% last 20 minutes, so we're great. The negatively charged oxygen is basically in the same position as this carbon-hydrogen bond. And so just as we did in the E2 reaction, we can have lone pair electrons on the carbonyl oxygen kick down into the antibonding orbital between carbon and the Y group, and the Y group leaves. And that gives us, restores the carbon-oxygen pi bond and gives us a molecule where our nucleophile has been swapped out for the Y group. Okay, so if you think about what we have done here, we had a nucleophile attack to generate a tetrahedral intermediate. And then, because the Y group was a better leaving group than the nucleophile, the negatively charged oxygen kicked off the Y group, and we ended up with a substitution product. Okay? Overall, the reaction went like this. We added a nucleophile, we replaced the Y group with the nucleophile. This type of reaction is called nucleophilic acyl substitution, but if you break it up into pieces, it's an addition step followed by a subsequent elimination step. Okay? So that's a huge class of reactions. We'll talk about some of them in chapter 13 and more of them again, I think, in chapter 15. All right, questions about that? Yes?
I know with the general acid catalysis, it generates an oxygen that's protonated. Is that not applicable to this type of reaction?
So in general acid catalysis, or even specific, you end up with a tetrahedral intermediate that is protonated. Does that apply here? Absolutely. So let me show you how that would be. Suppose you have a neutral tetrahedral intermediate. Then the question you ask is the Y group a better leaving group than, relative to what? Relative to neutral oxygen. That's the point of comparison here. And relative to the nucleophile. In other words, is this neutral oxygen reactive enough for its lone pairs to kick down and kick off the leaving group? And that can happen, and we'll see examples of that. A specific example where that occurs would be this. Here's a nucleophile, and let's suppose the leaving group was hydronium. So you're going to compare the leaving group, which would, in this case, would be H2O, versus a neutral oxygen. Conjugate acid of H2O is H3O plus, pKa of -2. The point of comparison is a neutral oxygen whose conjugate acid is ROH2 plus, pKa also -2. So yeah, comparable in leaving group goodness, and so lone pair electrons on the oxygen can kick down and that group can leave. Okay, we'll see examples of that. You may be asking, how on earth did we get hydronium there? Don't worry about that, we'll come to it later. Okay, what else? Okay, yeah?
Just a quick refresher question. So if the pKa is lower, depending on which pKa is lower, that will decide which leads.
Right. So we're really dealing we're really dealing with two questions here. First, compare the leaving group ability of the Y group and the nucleophile, and because then you'll know which of these two, if any, will leave. The second thing you have to ask is the oxygen either negatively charged or neutral strong enough to kick off either of these groups? Okay. An example of a case where the negatively charged oxygen is strong enough to kick off a leaving group would be this example. Let's have a methyl group here. Let's suppose the tetrahedral intermediate is this. Okay. And the nucleophile was that, and the leaving group is this. So think about what the nucleophile looked like before it attacked, or what it would look like if it left. Think about the potential leaving group and what it would look like if it left. Now we ask which of these is a better leaving group. To make that comparison, we draw the conjugate acid and compare pKa 16 and like -9 or something like that. So clearly the chloride is the better leaving group. That's question number one. The second question is this negatively charged oxygen strong enough internal nucleophile to kick off the leaving group? Notice what happens when that kicking off occurs. We trade a negatively charged oxygen for a negatively charged Y group. So if this negatively charged Y group is more stable than this negatively charged oxygen, then you expect this reaction to occur. All right? Sometimes, as I've explained this in the past, folks get confused. Why are we worrying about the pKa of this? Why are we worrying about this negatively charged oxygen? Does that leave or anything? No. We're just asking the question, is this leaving group good enough such that a negatively charged oxygen can kick it off? And we're basically comparing the stability of the tetrahedral intermediate versus the stability of these products. It's better to have a negative charge on chloride than on oxygen. Okay? Other questions? All right, that was scenario A, where Y is a good enough leaving group to be kicked off by the oxygen of the tetrahedral intermediate, and it's a better leaving group than the nucleophile. Let's deal with another scenario, and this is the scenario where Y minus is not a good leaving group, and relative to the nucleophile, and that Y minus and the nucleophile are not good enough to leave or be kicked off by the negatively charged oxygen. In that case, what happens is, what we're saying is, if Y minus is not good enough to leave, and the nucleophile is not good enough to leave relative to this negatively charged oxygen, then you're sort of stuck here. and the reaction is done, usually what happens afterwards in a subsequent step, we add water. In most organic reactions, after you do the reaction, you do something that's called aqueous workup. You'll learn about that if you take the 353 lab. But you add water and the tetrahedral intermediate gets protonated. Now it's neutral, and there you stay. And this is simply an addition product because we added the nucleophile but didn't do anything else. Let's do an example of that. Suppose our Y group is a hydrogen. Suppose we have an aldehyde, okay? And suppose we attack that aldehyde with what you will learn later on is an organolithium reagent. This organolithium reagent looks like it has a covalent bond between carbon and lithium, and in fact it does, but you can think of it as though it were just the negatively charged carbon. It's way more complicated than that, but in general it reacts like that, so we'll pretend it's that. The negatively charged carbon attacks the carbonyl carbon to create the tetrahedral intermediate. Of course, based on our consideration of the nucleophile attacks, that negatively charged carbon should be strong enough to attack directly. No acid catalysis needed. Our tetrahedral intermediate looks like this. The nucleophile was the methyl group. The leaving group is H minus. If H minus left, its conjugate acid is hydrogen, pKa. Oh shoot, I always forget what it is. I think it's in the 30s. I'll look it up at some point. CH3 minus, conjugate acid is methane, pKa like 50. So these are terrible leaving groups relative to that negatively charged oxygen. You would never expect the negatively charged oxygen to be able to kick off H minus. Why? This is not downhill in energy. A negatively charged oxygen is more stable than a negatively charged carbon. So we don't go on to do that. There's no subsequent elimination step. And we are stuck there until aqueous workup, where we protonate the negatively charged oxygen. Okay? Now, at some point in the future, the near future, we're going to show you a reaction where we react an organolithium reagent with an aldehyde. And some of you will be tempted to memorize, almost as though you're repeating a mantra to yourself. Organolithium reagents react with aldehydes to give secondary alcohols. But that's kind of, you don't need to do that. Like, seriously, don't do that, because if you understand the reactivity of carbonyl compounds and you know what your nucleophile is, you know how to assess what's going to happen to the tetrahedral intermediate, it falls out of those considerations what the product should be. You don't need to memorize that the product is a secondary alcohol, okay? You want to develop predictive power, not memorization power. Yeah?
I know in previous classes they've told us not to spend too much time memorizing pKas. Would you say that we should do that now, or should we memorize them in classes?
So yeah, the question is, should you memorize pKas? No, not necessarily. I will provide a pKa table for you. And it's ultimately, I think, if you're still at the point where you're looking up pKas to make this sort of comparison by the exam, probably you haven't had enough practice. I didn't really know these pKas until I started teaching the class, so I'm rattling them off just because they're sort of in my head. I don't expect you to be able to do that. You'll have access to a pKa table. It's useful to have a sense of an ability to rank nucleophiles, though, in terms of their reactivity. All right, what else? Okay. So finally, let's see. there's two other situations we need to deal with. One of them is the sort of dumb situation. What are you talking about? All of this is dumb. Well, no, this is an example of a reaction that you wouldn't do. This is where nucleophile is a better leaving group than the Y group. So as an example, oops, got our color scheme mixed up. Suppose you wanted to take this ester and react it with Cl minus to give you a tetrahedral intermediate. And I'm not even saying that this could happen because we've already talked about this probably being a weak enough nucleophile that it couldn't attack directly. But even if you could get here, your nucleophile attacks, you get to that tetrahedral intermediate. Who's the best leaving group? Cl minus, and so it just gets kicked off and nothing happens. This is the origin of the idea, the principle that your text talks about, that you can't make an acid chloride from an ester directly. Your text will say, oh, you can't make more reactive carboxylic acid derivatives from less reactive carboxylic acid derivatives without special reagents. And that's just a statement of this dumb situation case where the nucleophile you add is actually a better leaving group than the leaving group you have. Yeah?
So even if for a brief moment it does attach. And then
Say it louder.
Even for a brief moment it just attaches and then just immediately.
Right, I mean, even if you could get here, it would get kicked off directly, nothing happens. All right, folks, that's enough for us today. I'll see you Wednesday.